Hi everyone. So in this video we are going to discuss different parameters of OpAmp. So till now we haven't considered anything like offset voltage or offset current or CMRR or slew rate or frequency response, nothing like that. We just considered that the OpAmp can have a finite gain, it can have a finite input resistance, it can have a finite output resistance. But there can be other factors too. So these are those factors: input offset voltage, input offset current, output offset voltage, input bias current, CMRR, slew rate, frequency response of the op-amp. So one by one we will study. So first let's start with input offset voltage. So what is input offset voltage? So ideally if there is a op-amp, this is your op-amp, and you connect both of the terminals to ground. Both of the terminal of the op-amp are connected to ground. So what you would expect at the output? At the output, if differential voltage is 0, then what you would expect? 0 into the gain, that would be 0 only. So ideally you would expect output to be 0 volt, right? But practically it doesn't happen. You expected your output to be 0 volt, but practically you get some output. That output I can say output offset voltage. When both of the terminal of the input are connected to 0, still you are getting some output. If you connect both of the terminal to 0, you would expect your output to be 0. You just brought a op-amp from the market. You did not connect anything. You just connected both of the terminal to ground. Then at the output you would expect 0 voltage, but you would get some finite voltage there. It can be some millivolt, it can be some microvolt, but you would get certainly some finite voltage. So that is known as output offset voltage. That is the output offset voltage. Now why that happens? So here you put input equals to 0, all those inputs equals to 0. What does that mean? You put small signal input to the 0. Like this op-amp is running at the supply, no? This op-amp is running at the supply. So certainly the supplies are there and certainly there will be some DC bias. It can be VB1 and it can be VB2. So because of these DC bias, there can be some DC output. So that output is being appeared here. Look, if both of these DC bias were equal, then both of these DC bias were equal, then what would be your output? Output would be A into VB1 minus VB1. Your output would be equal to 0. But now these DC bias are not equal. These DC bias are different. And because of that, you get some voltage at the output. Okay, even if you haven't applied any input, even if you have not applied any small signal input. Look, do you remember the first stage of op-amp? It was a MOSFET amplifier, then there was a common source state, then there was a common drain stage, right? We studied it in MOSFET amplifier. When we studied the MOSFET amplifier, I told you how to make an op-amp, right? So initially there was differential amplifier, then there was this common source, and there was this common drain. So if your MOS is working, that means you have given some bias to voltage, no? You would have given some bias voltage to gate terminal of this MOS and gate terminal of the other MOS as well. So you have given some bias voltage. Now you did not apply any small signal input. You did not apply any small signal input, so you are not expecting any small signal output. You did not apply any small signal input, so you are not expecting any small signal output, right? But since there is a difference in the bias, let's just say this VB1 was 5 volt, but this VB2 was 5.001 volt. Because making these bias same is very tough task. When you practically design the op-amp, you cannot get 5 volt, and here also you can get 5 volt. This is very tough, right? So one is 5, one is 5.001. So what will happen? Because of this difference of 0.001, now this difference will act as small signal only. This is a small signal only. Now this small signal will be amplified. You did not apply any small signal from your own side, but since there is a difference in the bias, that is acting as a small signal only, and that is being amplified in the further stage of the op-amp. So there are a lot of stages. Eventually it is being amplified, and that is appearing at the output. So that is the issue, right? So now what you do whenever you use op-amp, so there will be a data sheet. If there is some IC, integrated circuit, I told you op-amp is IC only. So there will be some data sheet. There they will give you what is the offset voltage. So they will define some voltage. They will say that your offset voltage is 5 millivolt. What does that mean? That you need to apply 5 millivolt at the input before using it as an amplifier. If you are going to use it as an amplifier, do apply 5 millivolt at the input so that your output is 0. Did you understand this point? What did I say? even if we don't apply any small signal input, still we are getting some output. So to nullify that particular output, to nullify this particular output, we are applying some small signal voltage at the input side so that our output becomes 0. Say yes or no. And why we are getting this output? Because of the mismatch in the bias. Did you understand this whole point? I brought a OpAmp, I gave the OpAmp some bias, but I did not apply any small signal input. So I was expecting there will be no small signal output, but still I was getting some small signal output. Why is that so? Because of the difference in DC bias. Now to make that output equals to 0, I need to apply some input from my side at the input. At the input terminal, I need to apply some input so that my output becomes 0. And that input voltage is known as input offset voltage. Did you understand this point? This I have written on the next page, so you will be able to understand. So at the input terminal, you apply a small signal offset voltage to make your output equals to 0. So if I apply this small signal input voltage, then what I would receive is my output equals to 0 volt. Previously, I was receiving some output that was VOO, output offset voltage. I was receiving the output offset voltage, but since I have applied this VIOS, so that's why I am receiving output voltage equals to 0. Now what will be the polarity of this VIOS? That is very tough to predict. So you will always take offset voltage to be plus minus something. If in the question it is given that your offset voltage is 5 millivolt, then only you will take 5 millivolt. Otherwise you will say it will be plus minus 5 millivolt, because you are not sure if you are going to apply it here or here, at the negative terminal or at the positive terminal. So even if in the question they are saying that your offset voltage is 5 millivolt, still you will take it to be plus minus 5 millivolt. Because generally what we do is that we show the offset voltage. How do we show the offset voltage? We show the offset voltage. Generally, this is the way of showing the offset voltage. We apply a battery at positive terminal. This is how we show the offset voltage. Now the offset voltage can be plus 5 millivolt as well. It can be minus 5 millivolt as well. At this input, I am not applying anything. At negative input, I am not applying anything. But at the positive input, I can apply 5 millivolt as well, and I can apply minus 5 millivolt as well. So either 5 millivolt or minus 5 millivolt will make my output equals to 0. That's it. Okay, so that is known as input offset voltage. So ideally, I should expect that my output voltage should be 0 if I am not applying any small signal input voltage, but still I get some small signal output voltage because of the mismatch in the DC bias provided to the transistor of the OpAmp. And to nullify that particular output voltage, I have to apply some small input voltage at the input side of the OpAmp, and that input voltage is known as input offset voltage. And the range of that input offset voltage is typically between millivolt to microvolt. So I hope this concept is crystal clear to you, right? And what is the general way of showing a offset voltage? So it is tough to predict the polarity of the input offset voltage, because I told you it can be plus 5 volt as well, it can be plus 5 millivolt as well, it can be minus 5 millivolt as well. So generally we show it with the battery at inverting terminal. Now this offset voltage can be plus 5 millivolt, it can be minus 5 millivolt, it can be plus 1 millivolt, it can be minus 1 millivolt. So this is how it is shown. At negative terminal, I will not apply anything. At positive terminal only, I will apply the offset voltage. It can be plus 5 or it can be minus 5 as well. So remember it, the offset voltage can be both positive and negative. Okay, now we will solve a particular problem that will help you to understand it more deeply. So let's solve a particular problem. So this is the problem given to you. Now what we are trying to do, we are trying to see the effect of input offset voltage. This is what we are trying to do. So we have made an inverting amplifier with RF by R value of 100 volt. Now there is no offset. I do not talk about any offset here. Considering 0 offset, what will be your output voltage? Your output voltage will simply be minus RF by R, right? V0 by Vin would be minus RF by R. So you can say it would be minus 100. So what will be your V0? Your V0 will be minus 100 into Vin. Vin is 10 millivolt. So your V0 will be minus 1 volt. This will be your V0, right? But what if there is an offset voltage of plus minus 1 millivolt? So how will you show it? You will just copy this circuit. There is an offset of plus minus 1 millivolt. So I told you how to show the offset voltage. We will show it by a battery of plus minus 1 millivolt at the non-inverting terminal. So what I can do, I can apply the superposition theorem. I am applying the superposition theorem. So what will be my output voltage? So first I am considering only this 10 millivolt source. So if I consider this 10 millivolt source, what I will get? Minus RF by R into this 10 millivolt. Then I am considering this plus minus 1 millivolt. So what I will get? Plus. Now I am considering only this plus minus 1 millivolt. So this will be shorted. So now it is acting as a non-inverting amplifier only. So what will be my output? My output will be 1 plus RF by R into the offset voltage. Into the offset voltage. So here better I should write V in only. Okay. And this is my offset voltage. So did you understand this point? What did I do here? I applied superposition theorem. First I consider only V in. Okay, my handwriting is becoming bad because I am having a finger injury. So I hope you don't mind much of my handwriting. Okay, so I will try to write in a better way. Just a second. So it is minus RF by R into V in plus 1 plus RF by R into VIOS, right? Do you understand? You understood it? First I consider only V in, then I will get minus RF by R into V in, then I consider only VIOS, so 1 plus RF by R into VIOS. So what is the value of RF by R? That is 100. So minus 100, what is the value of V in? V in is 10 millivolt plus 1 plus RF by R. What is RF by R? RF by R is 100. And what is VIOS? It can be plus minus 1 millivolt, right? So it will be minus 1 volt plus 101 into 1 millivolt. So it would be plus minus 0.101 volt, right? 1 volt plus minus 0.101 volt, because this is 101 already and 1 millivolt, 0.101. So your output can be anything between, not between, your output can be either minus 1.1 volt, because if you take the negative case, if you take the negative case, if you take the negative sign, then what you will get? Minus 1.101, or it can be minus 1 plus 0.101, so it would be 0.899 volt. Minus 0.891 volt. So you expected your output to be minus 1 volt. Ideally, you expected your output to be ideally minus 1 volt, but it can be, sometimes it can be minus 1.001 volt, or it can be minus 0.899 volt. So that much error you can see. It is approximately how much error it is? 10% error, I guess, right? What is the 10% of 1? It is 0.1 only. So 1.1. No. It is not 10%. Sorry. It is not 10%. 0.1, 1.1. Oh, sorry. Here I should write 1.101. 1.101. So yeah, 10% error you can get in the output. 10% error, because you expected minus 1 volt, but you can get minus 1.101, or you can get 0.899, minus 0.899. So 10% error can be there. So in the output, you are expecting 10% error because of the offset voltage. So we analyzed it. So because of the offset voltage, your output may vary, right? So this was your input offset voltage. Now we are going to study about input offset current. So you have understood input offset voltage. So I will just give a brief review. So what did we see? Ideally, we should expect output voltage to be minus 1 volt, even if we are not applying any small signal voltage at the input. So what we should expect? Your output voltage should be 0, but because of the mismatch in DC bias, you are getting some output. So to nullify that output, you apply some offset voltage from your side at the input terminal. That input is known as input offset voltage. That input offset voltage can be shown as a battery at the non-inverting terminal only. The offset voltage can be both plus minus value. It can be plus 1 millivolt or minus 1 millivolt. Okay. Then we saw a question. So if there is no offset, then simply your output would be minus 1 volt. But if there is some offset, then because of that you will get some variation in the output. So that we have already seen here. So we have shown the offset by plus minus 1 millivolt at the positive terminal. So your output is varying between minus 1.1 to 0.89, right? So 10% error you can see here. Now we are going to see the input offset current and input bias current. Both of them we will see parallelly. So what is the ideal case? Ideally, we should expect 0 ampere current in the input, right? Forget about the output. This is output, so forget about the output. But ideally, there should be 0 ampere current in the input of the OpAmp, right? In the input of the OpAmp, there should be 0 ampere current. But practically, what happens? You get some bias current. Now it can be inward as well, it can be outward as well. The current can be going into or it can be coming out as well. So better I should show IB plus and IB minus. The current that is getting into plus terminal, the current that is getting into negative terminal. So there can be some current, there can be some input current. Why is that so? Because you haven't studied BJTs, I know. But those who have the basic idea of BJT is same as MOSFET only. But BJT drives some current. BJT is drive some base current. Okay. In MOSFET, what do we study? That gate current is 0, right? This gate current is 0. But BJTs drive some current. And this differential amplifier, what was the first stage we saw? That differential amplifier with active load, that can be made using BJTs as well. So in some OpAmp, the input stage is made from the BJTs, not from MOSFETs. So if that is made from BJTs, then it can drive some input current, right? So let's just call this one as IB1, this one as IB2. And since this is PNP transistor, so IB1 will be going outward. You don't need to worry much about the direction. When we study BJT, you will understand the direction of current. So if you haven't studied BJT, do not worry about the direction of the current. But it can drive some current. And practically, even the gate terminal of MOS can drive some current. Okay. Till now, from the first lecture of the MOSFET, we have always studied that the gate of the MOSFET cannot drive any current. But practically, the gate of the MOSFET can also drive some current. That is known as tunneling effect. But that is out of your scope from the interview perspective as well, from the gate perspective as well. So we are not going to discuss that. We are not going to discuss that even in device physics, because that is out of the scope of the syllabus. When we study EDC, at that time also we are not going to discuss that because that is out of scope. So let's not discuss about that. The main concern here was the input side can drive some current. That's it. Now there are these two currents. The directions can be different as well. It can be inward as well. It can be outward as well. So we defined some parameter. This parameter we defined. We call it as input bias current. So what is that input bias current? That would be IB1 plus IB2 divided by 2. That's it. Or better I should write IB plus IB minus divided by 2. IB plus IB minus divided by 2. This is your IB current. Okay. And what about your offset current? So the other parameter we defined was offset current. That was the difference of both of the current. So in the data sheet of a OpAmp, always these data will be written. What is your bias current? What is your offset current? What is your offset voltage? So these data will be written. Your offset voltage will be some 5 millivolt. Your bias current can be some, it is in microamp only. Let's just say it is 1 microamp. Your offset current is some 1 nanoamp. Okay. So what is the range? Typical range is, typically in OpAmp ICs, the range is from microamp to nanoamp. This is the range. Okay. So these are the definitions that are defined. The input bias current is the average of both of the current, and input offset current is the difference of both of the current. That's it. Well and good. So ideally, the input of the OpAmp should drive 0 ampere current, but practically the input of the OpAmp drives some current. They drive some current, and if they are driving some current, so we have to show them. Now the current direction can be some different. It can be inward as well. It can be outward as well. So we defined a particular we defined a particular parameter. So we are calling that parameter as input bias current. That is the average of the both of the current, IB1 plus IB2 divided by 2. Then we are defining the other parameter, that is the difference of the both of the current, and then we are taking the magnitude. So it will always be a positive value. We are taking the magnitude, IB plus minus IB minus. So after that we are taking the magnitude. So it will always be a positive value. So this is what these two parameters are defined. Well and good. Let's see more about it from a question. So this is the question given. We are seeing the effect of bias current. So considering a non-inverting amplifier, the same question is there. What will be your output voltage? Minus RF by R. There is no offset now. There is no offset current. There is no offset voltage. So ideal case is there, which we have already solved. So what was the output voltage you were getting? So minus 100 into 10 millivolts. So you would get 1 volt at the output. But now you are having some offset, some bias current or offset current. Okay. So they have given the IB1 and IB2 are both are 1 nanoampere. Both are 1 nanoampere. This is also 1 nanoampere and this is also 1 nanoampere. IB1 and IB2 both are 1 nanoampere. RF is 100 kilo ohm and R1 is 1 kilo ohm. The same circuitry is there. RF by R is 100 only. RF by R is 100 only. But to solve this particular problem, I need the value of RF as well. So this value I have given here. RF is 100 kilo ohm and R is 1 kilo ohm. IB1 and IB2 are 1 nanoampere. So what will be your output voltage? Again, you can apply nodal analysis. Again, you can apply superposition. Superposition I am applying. First, I will see the effect of only this V in. No effect of these currents. So I am considering these currents are 0. I am applying superposition theorem. So I am considering these currents are 0. That's it. Okay, so only I am considering this voltage source. So what will be your output? Output will be minus RF by R into V in. So that would be minus, I can write it in theory as well, minus RF by R into V in. Plus, now I am not considering this input voltage source, so I am considering it to be ground. If that is ground, now I am considering both of the current sources. Tell me, will this IB2 have any effect? Will this IB2 have any effect in the output voltage? No, it will not have any effect. It is going into the positive terminal. That's it. Okay, no worries. The gain of the OpAmp is infinite. So virtual short is valid. This node will be 0 only. If this node is 0, this node is also 0, this node is also 0. So there is 0 ampere current. Because I am applying superposition theorem, so I am only considering IB1 and IB2. This node is 0, this node is also 0. So 0, 0, there is 0 ampere current here. So this IB1 is flowing like this. Right? This IB1 cannot go here. There is no component of current here. So the current IB1 that will be flowing in the feedback loop only. The complete current will be flowing in the feedback loop only. So this IB current will give the drop like this, right? So what will be your V0 voltage? V0 voltage will simply be IB1 into RF. That's it. There is no effect of IB2. Did you understand this point? There is no effect of IB2 at all. IB2 put no effect here because it was going into the positive nodal. Okay, it has no relation with V0. There is a negative feedback involved. There is a negative feedback involved, and the gain is also infinite. So this 0 is copied here. If this 0 is copied here, then this IB1 is completely flowing in the feedback loop because this R resistance is driving 0 ampere current. I am applying superposition theorem. This V in is gone. So this complete IB1 is flowing through RF. So V0 voltage is IB1 into RF, right? So this when we are applying the superposition theorem, but we are showing it completely. So this is how we will show it, right? So IB1 into RF. So minus RF by R minus 100 by 1K into V in, that is 10 millivolt, plus IB1, that is 1 nanoampere, into RF, that is 100 kilo ohm. So it is 10 to the power, this will be minus 1 volt, right? Now this is 10 to the power 5 and this is 10 to the power, this is very low value. So this will not be giving that much of effect. So I should take IB1 and IB2 be 1 microampere instead, so that in the output at least we get something, right? This is 1 microampere. This is 1 microampere. 1 volt plus, and this is 1 micro. We are taking it to be 1 microampere. So what we will get here is that 1 micro into 100 kilo ohm. 10 to the power 6 into 10 to the power minus 10 to the power minus 6 into 10 to the power 5, it will be 0.1. So your output voltage will be minus 0.9 volt. Now in this question they have given the direction of IB1. They have given the direction of IB1. but they can avoid giving the direction as well. They can only say that bias current are 1 microampere. Both of the bias current are 1 microampere. Now you don't know the direction. If you don't know the direction, your answer will be -1 plus minus 0.1. So at the output, you can receive -1.1 as well or -0.9. Are you getting this point? In this particular question, they have given the direction that 1 microampere current is going in. It can be coming out as well. If it is coming out, then your output can be these two values. It can be coming in or coming out. If it is going in, then this is your output. If it was coming out, then this would have been your output. So here in this case, it is already shown. That's why we are writing the output voltage equals to -0.1. If it was not shown, then we would say that there can be two possible output, this or this. Right? Understood? So because of the bias current, we are getting this particular output -0.9 volt, but we were expecting output to be -1 volt. Well and good. Let's see more questions. So in this particular problem, simply the currents are shown 1 milliampere, 2 milliampere. You just need to find the output voltage. That's it. These are the bias current that are shown, 1 milliampere current, 2 milliampere current. Just tell the output voltage. This is your question, nothing else. So what is your output voltage? What do I do? I am not applying superposition theorem now. The same question is there. It is exactly the same question. I am not applying superposition theorem. I can apply superposition theorem as well. But what do I see? This 2 milliampere will have no effect. That is going into the positive terminal. Forget about it. This 0 will be copied here. There is no doubt about that. This 0 will be copied here. From here to here, this 0 will be copied because there is negative feedback and the gain of the OpAmp is infinite. The gain of the OpAmp is infinite. So certainly negative feedback is valid. I told you when the virtual short is not valid, only three conditions are there. Output is saturated. Output is saturated. No. There is positive feedback. Is there any positive feedback? No. The gain is finite. The gain is finite. No. The gain is also infinite. So certainly the concept of virtual short is valid. Right? The concept of virtual short is valid. So 0 minus, I am applying nodal at 0. 0 minus 1 by 1k. Plus this current is also outward. 1 milli. Plus 0 minus V0 by 2k is equals to 0. So V0 here we are getting is 0 volt. So just I applied nodal. You can apply superposition theorem as well. If you had applied superposition theorem, what would be your output? If you had applied superposition theorem, so how would you write your output? So only considering this 1 volt source, what would be the output? Minus RF by R, 2k by 1 into 1 volt, plus only considering this 1 millivolt and only considering this 1 milliampere and 2 milliampere, what would be the output? This VIN will be shorted, so this will not drive any current. So this complete 1 milliampere will be flowing through this resistance. So your output will be, 1 milliampere is flowing through this resistance. So your output will be 1 milliampere into 2 kilo ohm. That would be plus 2 volt only. So 2 kilo ohm into 1 milliampere. So minus 2 plus 2, 0 volt. So V0 would have been 0 volt. Well and good. So this is how you could calculate it. So this was a very easy question. Let's see one more interesting problem. It will give you, look, we have discussed about IB1, IB2, but we did not discuss about IB. What was your offset current? Which was actually, what was your bias current? It was actually IB1 plus IB2 by 2, input bias current. And what was your offset current? That was IB1 minus IB2 mode. So why did we define these parameters? What is the use of these parameters? So that we are going to see now. Okay. So we are going to see that with a particular question so that you understand it better. So you need to find the output voltage. This is your question. That's it. You need to find the output voltage. Now there is a resistance connected this time. There is one resistance connected. So IB1 is the input bias current. IB2 is also input bias current. So this same IB1 will be flowing through RC as well. This same IB2 will be flowing through RC as well. So it would give a voltage drop like this, right? I'm calling this voltage drop as VC. So what is your VC voltage? VC voltage is minus IB2 into RC. Say yes or no. Do you agree to my point? My VC voltage is minus IB2 into RC. Now this same VC is copied here, right? No doubt about it. What did I say? There is IB1 current as well. There is IB2 current as well. In the previous questions, what was the scene? That it was grounded. It was grounded. So IB2 was making no impact. But now we have connected a resistance. We have connected RC resistance. Why did we connect it? That we will get to know. In the final expression, we will get to know why did we connect it. But for now, we have connected it. So there is a voltage drop across RC, and that voltage drop is VC that I am saying. That is minus IB2 into RC. So this is the equation 1 that I am assuming. Okay. So now this VC is copied here. So what will be your output voltage? Output voltage will be VC by R plus VC minus V naught by RF. VC by R output current, VC minus V naught by RF output current plus IB1 is equals to 0, right? So what I can write, VC by R plus VC by RF plus IB1 is equals to V naught by RF, right? Now VC, what is VC? VC I am taking common. VC is minus IB2 into RC. VC is minus IB2 into RC. Minus IB2 into RC into 1 plus R, 1 plus RF plus IB1 is equals to V naught by RF. Then simply this RF you can take here in the multiplication. So this complete value minus IB2, or you can write down, कैसे लिखूं, ऐसे लिख देता हूं, this is IB1, this is being multiplied, RF is coming here, that's it. I put VC value, that is minus IB2 into RC, then 1 by R plus 1 by RF, that is common, plus IB1, then this RF is multiplied here. This RF is being multiplied with this complete factor. So this is your output voltage. This is the answer of the first question. This was the answer of the first question. You did not understand anything here, just you got the final answer. Now what is the second question is saying, that if RC is equals to R plus R parallel with RF, if RC is equals to R parallel with RF, if RC is equals to R parallel RF, parallel combination of these two resistance, if RC is equals to R parallel RF, so what will happen? This RC can be replaced with R parallel RF. This RF is there, then minus IB2, or better I should write minus IB2, this RF I am again taking here, okay, and RC is R parallel RF, so you can write R into RF upon R plus RF. This is the parallel combination. Now you can solve this bracket. What will be this bracket? This bracket would be R into RF upon RF plus R plus IB1 is equals to V naught by RF, right? This and this get cancelled. So what you are getting at the output? You are getting at the output is RF into IB1 minus IB2. Can you write this IB1 minus IB2 as offset current? So RF into IOS. Yes or no? Right? So this is the output voltage you are getting. And if, so this was the first condition you took, if this was equal, and if IB1 and IB2 both were equal, IB1 is equals to IB2 is equals to IB. If both were equal, then what would be your output voltage? Then your output voltage would have been 0 volt. Why so? Because IB1 minus IB2 would be 0 only. So 0 into RF, your output voltage would have been 0 volt. So what did you understand here? Why did we apply this compensation resistance? If this compensation resistance was not there, then what was the output you were getting? We are only considering the effect of offset current. So what was the output we were getting? IB1 into RF. Now since you connected this compensation resistance, what is the output you are getting? IB1 minus IB2 or IB2 minus IB1? IB1 minus IB2. This is the output you are getting, right? Previously you were getting this output. If this compensation resistance was not there, this was the output. If you connect this compensation resistance, this is the output. And luckily in the OpAmp, if both of the current are equal, then because of the bias current, you are getting zero output only. And this is what you want. You don't want any output because of the bias current. Bias currents are introducing an error only, no? Here you expected -1 volt output, but you are getting -0.19 output. You expected -1, but you are getting -0.9. So that is an error. 10% error is there. So bias current, bias voltage, or this offset voltage, all these voltage are contributing in an error. You want to reduce that error. So previously you were getting this output, but now IB1 minus IB2 will certainly be lesser. Let's just assume IB1 is 50 micro and IB2 would be some 52 micro. So it would be 2 micro into RF, and here you are getting 50 micro into RF. So you have reduced the error, and luckily if both current were same, then the error would have been 0. So this compensation resistance is connected to reduce the error. Are you getting this point? Also you will remember the value. The remember value is R parallel with RF. And also you will remember one more result. What is that result? That if both of the bias current are equal, then if both of the bias current are equal and if that compensation resistance is there, then your output voltage will be 0. I will write down the conclusion. It will be more clear to you. I will write down the complete conclusion. I will draw 3 circuits and it will be crystal clear to you. So let's copy this circuit first. What is the conclusion we are getting? This is the circuit 1. The circuit 1 says forget about it. And in the circuit 1, what I am doing is I am connecting it to ground. There is no compensation resistance. So if there is no compensation resistance, so simply what is your output voltage? Forget about this. So your output voltage is IB1 into RF. This is your output voltage if there is no compensation resistance. Now in the second case, what did you do? You connected a compensation resistance. So if you connected a compensation resistance, where RC is R parallel with RF. If you have connected this compensation resistance, then what is the output you are getting? The output you are getting is I offset into RF, right? So generally what you can do is, if the compensation resistance is connected, and in the question they have given the offset current, they have just mentioned that offset current is given, then what you can do to solve the problem? You can consider that offset current is flowing like this. Say yes or no. And there are no other current, just the offset current is there. Forget about this IB1 and IB2. Just to solve the problem, this is the easiest method I am telling you how to solve a particular problem in the examination. You see the circuit, you see that compensation resistance is connected. In the question they have given you the offset current value, that is IOS. So what you would do, don't consider any bias current, nothing like that. Just consider a offset current, that is IOS. So you can directly write the output voltage. Did you get this point? Say yes or no. And if they give the, if you don't want to solve like that, you can solve by simple method as well, by applying these equations the way we have applied here. But just to solve the problem quickly, what you can do, compensation resistance is there, so you got to know that if compensation resistance is there, so my output will be the difference into these two current into RF. That's it. And these kind of questions are asked very often with the same circuitry. So that's why I am asking you to remember. But if you don't want to remember, it is also fine. But the offset is generally shown in the feedback. That's it. And what is our third circuit? Third circuit I will also make. What I will do there is that I will just copy this circuit. So this is going to be my third circuit. There what I'm going to do, these bias current are same this time. What will be your output voltage for the third circuit? This is the output voltage for the second circuit. This is the output voltage for the first circuit. And what will be your output voltage for the third circuit? That will be 0 volt, because both of the current are equal. So if there is compensation resistance is there, then your output will be 0 volt, right? We have derived it as well. And this is also, you need to remember what is the value of this compensation resistance, that is R parallel with RF. This resistance parallel with this resistance. We will solve one more problem, it will be more clear to you. So one more problem to make your concept more clear. So this particular question is given in front of you. The value of R, RF is given, everything is given. RC value, this compensation resistance value is also given. I'm not saying this is compensation resistance, this is some resistance. This value is given to you. Input offset voltage is given 0.5 millivolt. They have given input offset current. Input offset current is 50 nanoampere, and input bias current is 100 nanoampere. Did they show any direction this time? Did they show any direction this time? This is my question. No, they did not show any direction, right? There is no direction of the current. So can you tell me what will be the current here? What will be the current here? One thing I can certainly tell, that these two currents are not equal. Why so? Tell me. Why I can say that these two currents are certainly not equal? Because there is input offset current is there. If both of the current were equal, then what you would have got? IB1 and IB2, then you would have got answer to be 0. But certainly offset current is there, that means both of the current are not equal, that's for sure. These two currents are not equal. Certainly one current will be 150 nanoampere, other one would be 50 nanoampere. Why so? Because the difference is 100. And what is bias current? Look, let's just say first current is X, the other current is Y. So what will be your offset current? X minus Y. That would be 50 nano. And what will be your bias current? That would be X plus Y by 2. And that is equals to 100 nanoampere. If you solve this equation, what you get? X equals to 150 and Y equals to 50 nanoampere. Now which current is what? It can be 100 nanoampere, it can be 50, or it can be 50, or it can be 100. Anything can be there. Sorry, 150 and 50 is there, no? So it can be 50, or it can be 150, or this can be 50, or it can be 150. Which current is what, you don't know. So you can't assume any current, right? But you know one thing, that there is compensation resistance is there. This compensation resistance is connected. So because of the bias current, at the output I am only going to have IOS into RF. That's it. There is no use of this. Did you get this point? You don't need to do these calculations. Nah, you don't need to find these currents. You don't even know the direction. Nothing else you don't know. You don't know anything. But you know one thing, that compensation resistance is there. If this compensation resistance is there, what is the value of compensation resistance? That is R parallel with RF. 9K into 1K divided by 10K. What do you get? 900 ohm. So if this compensation resistance is there, that means what it will give me at the output? It will give me at the output IB1 minus IB2. Which one is IB1? Which one is IB2? You don't need to care about that. IB1 minus IB2 into RF. And difference of these two current is certainly the offset current into RF. That's it. This is what it will give me. Here, if I am calculating the output voltage, what I will write? What will be my output voltage? 50 nano into RF. Because of the only offset current. Because of the offset current only I am asking. What will be my output voltage? 50 nanoampere into RF. RF is 9 kilo. So 9 kilo. Whatever we get, it is 5 into 10 to the power minus 4 into 9 into 10 to the power 3. By 10 to the power minus 4, it is 10 to the power minus 8. So 45 into 10 to the power minus 5 we are getting. So is that answer correct? This is my question. Is that answer correct? No, you should put plus minus. Because who knows the offset volt, this current is more, this current is lesser. Or this current is lesser and this current is more. You don't know, right? So here you will put plus minus. The offset current is given positive. The offset current that is given is positive. But the output, you don't know whether it will be plus or minus. right? This particular expression, whether it will give you plus voltage or minus voltage, you don't even know the direction of current. What is the direction of current? It is the input current or output current? You don't know. It is going in or going out. You don't know anything. So you will always put plus minus sign there. Okay, I have seen many teachers and even many students doing this mistake, that they say that offset current is 59 nanoampere. Then they just said that here the current will be flowing and your output is 50 nano into that 9 kilo ohm because of the offset current. That is absolutely wrong. It will be plus minus there. Okay, so did you understand this concept? We saw this particular problem. There was no direction of current given. In most of the question, it is certain that they will give you the direction of current and they will give you the values as well. Then the question will be easier, right? Why that question will be easier? Because we have solved it. The direction, everything was given, so we could solve it very easily, right? By the simple concept of network analysis. But here they have made the question like this. So they want you to waste your time in finding these current values, but we are not going to do that, because we know that the compensation resistance is given there. So my output voltage, because of that offset current, that would be I offset into RF. That's it. This is what I know. Well and good. So let's write down the output voltage now. Final output voltage we are going to write. Okay, so what will be the output voltage? First I am going to consider only the input voltage. Where is this is V in. Is that shown here? V in value I did not even give. I forgot to give the V in value. I should have given the V in value. Let's just say that is 1 millivolt. Okay, I should have given the V in voltage. V in is 1 millivolt, that is not given. So I have given the V in voltage. So I am only considering V in. There is no bias current. If there is no bias current, that means I am taking these currents to be 0 ampere. 0 ampere, right? No bias current, nothing I am considering. I am considering all the ideal case, right? So better to help you understand better, I would solve all the condition one by one. So let's copy this particular circuit. So applying superposition. Applying superposition. So first is considering only V in. I should first copy the circuit. Considering only V in. So if I am considering only V in, that means that only I am going to consider 1 millivolt, and my output I am calling as VO1. So here I am going to consider 0 ampere current. This is also 0 ampere current. There is no offset voltage as well. No offset voltage, no offset current, no bias current, nothing. Simple case. So what will be my V01? V01 will be 1 plus RF by R, because it is a non-inverting amplifier. 1 plus RF by R into 1 millivolt. What is the value of RF by R? RF by R is 10. So RF by R is 9, sorry. RF by R is 9. So you are going to get 10 millivolt. This is your V01, right? Now, what is the second thing we are going to consider? This question will clear your concept from the scratch. Now I am going to consider only the offset voltage. So considering only offset voltage. What did I tell you? How do we show the offset voltage? Offset voltage by connecting VIOS, here, VIOS here at the, and that is given as 0.5 millivolt. So here also you should take plus minus 0.5 millivolt. Now this current will be 0 ampere only, right? 0 ampere, and this current will also be 0 ampere. This output I am calling is V02. Previously I wrote V01. So what will be my V02? V02 will be 1 plus RF by R into 0 plus minus 0.5 millivolt. So 1 plus RF by R value was 10. So here I am getting plus minus 5 millivolt. This is your V02. This came considering offset. And now what is the third one and the last one? That is considering bias currents, bias and offset current. So I told you what is the way. We are not going to consider anything here. This is the RC. So these will have IB1 and IB2, but the output I know what I am going to get. For this particular circuitry, I know what is the output I am going to get if there is bias current. So what will be that output? Certainly the current will be flowing like this. So my output will be plus minus IOS into RF. What is my offset current? That is 50 nano plus minus 50 nano ampere into RF. RF is 9 kilo ohm. 5 into 10 to the power minus 8, 10 to the power minus 3. 45 into 10 to the power minus 5 we are getting, right? Volt, or you can write 0.45 millivolt. This is your V0 and plus minus sign is there. So what is the output voltage you are getting? This I am calling V03. V03. So what is your final output? V0 is V01 plus V02 plus V03, and that is first we are getting 10 millivolt, then plus minus 5 millivolt, 10 millivolt plus minus 5 millivolt and plus minus 0.5 millivolt. Now they can ask you, this is your final output. That's it. Now they can ask you what will be the V0 maximum value and what can be the V0 minimum value. So what will be V0 maximum? V0 max. What will be V0 max? Tell me. That will be 15.45 millivolt, right? And what will be V0 min? V0 min will be 5.45. So it would be 10 minus 5.45. It would be 4.55. 4.55 millivolt, right? So these two cases we have considered, V0 max, V0 min. Now in between also there can be two more values. What values they will be? 10 plus 5 minus 0.45. So what it will be? 14.55, right? This is one of the value, and one more value can be there, 10 minus 5 plus 0.5, because you don't know the sign. Plus 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 minus minus plus minus minus, any sign can be there. So these two values also you will get 5.45. So typically one of the output value you will get, either it will be 15.45 or 4.55 or 5.45 or 14.55. You don't know the direction, because in the circuit they did not show any direction. They just gave the data from the spec sheet only. There was the spec sheet given, data sheet was given. They just picked the data from there, they made the circuit, and now they are asking you what can be the output voltage. So this is how you will show it. This can be our output voltage. So maximum you can get 15.45, and sometimes you can get 5.45, depending on how the currents are flowing, how the offset voltage is there. Well and good. So I hope you must have understood the deep concept of offset voltage, offset current, and bias current. So if you have already studied this topic, I firmly believe that now the concepts are already clear. Now the concepts are crystal clear. Previously, I know this topic is not taught in that much depth. People are so much confused in this topic, but now it is all clear. Let's revise it once again from top to bottom. So how did we start? We started with offset voltage, output is not equal to 0 even if there is 0 voltage supply, 0 small signal input supply. So to make that output voltage equals to 0, we have to give some offset voltage at the input. That is shown as the supply at the positive terminal. It can be both positive and negative. So we saw the effect here. We saw the effect that there is 10% of error. Then we saw the bias current effect, that ideally it should be 0, but sometimes in the cases you can get some bias current. Not just in BJT, in MOSFET as well, there can be some bias current. Gate can also drive some current because of some known idealities. Right? The range is microampere and nanoampere. So two parameters are defined. One is the average, other one is the difference. Right? So these two parameters are defined. If there is no compensation resistance is connected, so simply your V01 would be IB1 into RF. That's it. Right? And we saw some particular question as well, how it is giving the error. So again, here it is giving 10% error, right? But now this question was very easy. So here also we got V0 equals to 0 volt. But now if there is compensation resistance connected, this RC compensation resistance is connected. Initially we don't know this value, we just put it to be RC equals to compensation resistance only. Then we got some particular voltage. Then we go to know if RC is R parallel with RF, parallel combination of these two, then what will happen is that your output voltage will be very, very low. It will be IB1 minus IB2 into RF. This should also be highlighted. It would be IB1 minus IB2 into RF. And luckily, if both of the bias current are equal, then your output voltage will be 0 because of the offset. So because of the offset, you are getting 0 error if you connect this compensation resistance. And that will happen if both of the bias current are equal. If both of the bias current are not equal, then what will happen? You will get the difference. You will get the difference at the output. And that will also be very, very low. So eventually you are connecting this compensation resistance so that because of the offset you get minimum voltage at the output. So these three cases we saw. If there is no compensation resistance, IB1 into RF. If there is this compensation resistance is connected, so V0 will be IOS into RF. Compensation resistance is connected and both of the current are equal, then output voltage will be 0 volt. Well and good. Then we saw this particular problem. Here we saw that offset current is given, bias current is given. So what is this bias current? That is IB1 plus IB2 by 2. And this, what is this offset current? IB1 minus IB2 and the mode. But you don't know what is the direction of current, nothing you know. But you know one thing, that compensation resistance is connected. If that compensation resistance is connected, that means it will reduce the output because of the bias current. So forget about the bias current first. First we calculated only for the Vin and only for the offset voltage. That is very, very easy. Then we thought about bias current. So when we thought about bias current, we got to know that my output voltage will be IB1 minus IB2 into RF. So simply it will be offset current into RF, but I don't know the sign, so there will be plus minus sign. That's it. So 10 millivolt plus minus 5 millivolt plus minus 0.45 millivolt. This will be my output. So I hope the concept is crystal clear now. So we have studied offset current, input offset current, input offset voltage, output offset voltage, and input bias current. Now we are going to study about CMRR, frequency response, and slew rate. These three parameters are also important. The voltage swing we have already seen. What do I mean by voltage swing? That output can be between plus Vset to minus Vset only. Output will rise, then it can be between plus Vset to minus Vset. So that is the voltage swing that we have already studied. So a lot of things we have seen. Now three things are remaining that we will see. Okay, in the next lecture we will try to complete those three things. Okay, then thank you. Hi everyone. So in the previous video we studied about offsets, right? We studied about input offset current, we studied about input bias current, we studied about input offset voltage and output offset voltage as well. Now what are the things remaining? CMRR, slew rate, and frequency response. So first we are starting with frequency response. So ideally what we have studied, that OpAmp always provides a gain A. This is what we have studied, right? What was the transfer function? It will always provide a gain A, irrespective of the frequency. So V0 S by VDS, this is a differential voltage. So V0 S by VDS is always A. This is what we have studied. It will always provide a constant gain, right? So ideally, what should be the frequency response? Frequency response means with respect to the frequency, how is the gain? So here I am writing gain in dB. Gain in dB. Because frequency response is always gain always in dB and frequency in omega. How should be the frequency response? Frequency response would be a simple line parallel to x-axis, because always it should provide a gain A, 20 log 10 A. This is the ideal case, but practically it does not happen. practically the response of OpAmp is same as the response of low pass filter. So OpAmp gives the response as low pass filter. Why is it so? In OpAmp there are some compensation capacitors. Look, I told you the internal structure of OpAmp. No? First active load amplifier, then there was a common source, then there was common drain. But that was not the complete one. Did I tell you anything about biasing? No. Did I tell you anything about stability? No. Because that is out of the scope. Out of the scope of interview as well, even at B.tech, M.tech level, and out of the scope of gate as well. That's why I did not tell you anything about that. But internally there are some capacitance as well. If I need to teach it, someday I will teach it, but on YouTube only. That is out of the scope for interview preparation as well, for gate preparation as well. But someday if I want to teach it, I will certainly teach it. There will be some compensation capacitance connected. Because of that capacitance, this is how you can assume the response. Like this is our OpAmp, and at the output you can assume some finite resistance. It will have some finite output resistance as well. It can have some finite input resistance as well, but that I did not show. So at the output you can assume one capacitor. So this is like on a crude level, on a block level you can assume it like that, right? That at the output you have some capacitance. So how will your response look like? So what I can write? What will be my V naught S? Can you tell me? It would be AV into VDS divided by R naught CS plus 1. I am writing the frequency response only from here to here. V naught S would be, what will be V naught S? V naught S would be 1 by CS upon 1 by CS plus R naught into the input voltage, AV into VDS. AV into VDS, right? So V naught can be written something like that, AV upon R naught CS plus 1. But till now you should have the practice to write it directly, not by this. Okay. So yeah. So what will be your V naught S by VDS now? V naught S by VDS is AV upon R naught CS plus 1. I can write it in that manner, S by omega naught plus 1, where omega naught is 1 by R naught C, right? So this is the actual frequency response of OpAmp, right? So how will the frequency response look like? What was the transfer function we got? V naught S by VDS. I can write it as TS. The transfer function is DC gain, some DC gain divided by S by omega naught plus 1. So DC gain is AV, but at omega naught you are having a pole. So what kind of response is that? That the response is same as low pass filter. So here I am writing gain in dB. And here this is the frequency. How will the response look like? Initially the gain A, but at omega naught you encounter a pole. So then you will have 20 dB roll off. So here you are having 20 dB roll off. This is the response of OpAmp. 20 log 10 A. So we thought that ideally it should be same gain for all the frequencies, but only for the range of omega naught it provides this gain, otherwise the gain will start rolling off. This is 20 dB per decade. Actually this is the body plot. How will the exact plot look like? I hope you guys have the idea. How will the exact plot look like? So for that you need to write T of j omega divided by, I am writing the magnitude, so it would be root omega upon omega naught whole square plus 1. As I replaced with j omega, so what is the magnitude of the lower value? 1 plus omega upon omega naught whole square. So how will the exact plot look like? Here I am only writing gain in decimal, not in dB this time, versus frequency. So at 0 frequency, if omega goes to 0, your gain would be AV only. At omega goes to 0, your gain is AV. After that, it will decay down like that. And what is your 3 dB frequency? 3 dB frequency would be not here, I should write it here. 1 by R naught C. This will be your 3 dB frequency. Omega naught I can say. So here what will be the gain? AV by root 3. Because at 3 dB the gain is 1 by root 3 of the maximum gain. Right? So this is the exact float. So this is the frequency response of our OpAmp. Now do you remember, if we connect a feedback, if we connect a negative feedback, let's just say my gain is A, here my gain is AV, my 3 dB bandwidth is omega naught. If I connect a negative feedback, what will happen? What will be my gain? Gain will be AV upon 1 plus AV into beta. And what will be my 3 dB bandwidth? Do you remember it? 3 dB bandwidth increases omega naught into 1 plus AV beta. I hope you remember it. The gain will be reduced by a factor of 1 plus AV beta, and bandwidth will increase by a factor of 1 plus AV into beta. In the feedback topology, we studied about it, right? If you don't remember it, still we can derive it once again. We will solve a problem in the next slide, and then we can derive it again. Okay, so for the given OpAmp, the open loop gain is 10 to the power 5. Open loop gain is 10 to the power 5. And your open loop cutoff frequency is 8 hertz. So F open loop cutoff frequency is 8 hertz. I can write what will be my omega naught? 16 pi radian per sec. So how will my open loop response look like? How will my open loop response look like? So I should not better write it as A only. So how will my open loop response look like? Open loop response will be, you have a DC gain of 10 to the power 5, but a cutoff frequency of omega naught. I'm not putting the value of omega. I'm just putting it S by omega naught plus 1. This is how my open loop response will look like. Say yes or no. Where omega naught is equals to 16 pi radian per sec. Now you connect a closed loop configuration, and they are asking you the voltage gain of this particular amplifier at 15 kilohertz. All this information is for this one. Here you can write the response is AVS. But what will be your V naught S by VNS? Can you tell me directly? What kind of amplifier is that? Voltage amplifier. For voltage amplifier, what is the gain? A upon 1 plus A beta. Right? This much you should remember. Or even if you don't remember, you can derive it. This point will be beta V naught. So V in minus beta V naught into AVS is equals to V naught. What I mean to say is that V in S minus beta V naught S into AVS is equals to V naught S. So if you derive V naught S by V in S, what you will get? AVS upon 1 plus AVS beta. This is what you will get. Where what was the beta? Beta was 1k upon 1 plus 79k. 1k upon 1k plus 79k. And that would be 1 by 80. That will be your beta. Well and good. Everything is crystal clear now. So I'm just putting V naught S by VNS. This is the gain they were asking. I am writing it as AVS with feedback. AVS with feedback. This is how I am writing it. So what is the value of AVS? That is 10 to the power 5 divided by S by omega naught plus 1. 10 to the power 5 divided by S by omega naught plus 1. Then whole divided by 1 plus AV beta. 1 plus 10 to the power 5 S by omega naught plus 1 into 1 by 80. Right? Any issue? No issue. So now what I can write it, 80 into 10 to the power 5. So this will be 5. Okay. divided by 80 into s by omega naught plus 1 plus 10 to the power 5. This is the response you are getting, right? No calculation error is there. No issue. Yeah. So this is the response we are getting. Here I am writing AVS with feedback. The response is 80 into 10 to the power 5 whole divided by 80 into. Let's just write it in terms of frequency. So here I am writing AV of j omega. In terms of frequency, I am writing j omega upon omega naught plus 1 plus 10 to the power 5. Now, where they are asking you the gain? They are asking you the gain at 15 kilohertz. What is the value of omega naught? 16 pi. But I am going to put f naught value only, because I can replace this j omega by omega naught by jf by f naught. Look, what is written j omega by omega naught? What I can write? J into 2 pi f divided by 2 pi omega naught. That would be jf by, sorry, 2 pi f naught. That would be jf by f naught, right? So this is what I am going to do now. So AV of jf with the feedback 80 into 10 to the power 5. So 80 divided by j f by f naught plus 1 plus 10 to the power 5, right? I need to put f value is equals to 15 kilohertz. F value is 15 kilohertz and f naught value is 8 hertz. So gain at 15 kilohertz with the feedback. So 80 into 10 to the power 5 divided by into j 15 kilohertz divided by f naught. F naught is 8 hertz plus 1 plus 10 to the power 5. Now you just need to find the magnitude. You just need to find this magnitude. That's it. So what I can see here is that this 80 will be multiplied here. So what I will get if 80 is multiplied here? So 15 into 10 to the power 4, right? This 80 is being multiplied. So j 15 into 10 to the power 4 plus 80 plus 10 to the power 5. This is what I am getting, and I need to take magnitude of this. Now this will be 80 into 10 to the power 5 divided by under root 80 plus 10 to the power 5 whole square plus 15 into 10 to the power 4 whole square. I will bring the calculator and will write down the answer. So here if we solve this particular expression, you will get 44.36 volt per volt. So this was the exact answer. This is the gain we are getting, right? This is the gain at that particular frequency. Okay, so this was the problem. What was given? First we found out the open loop transfer function. This was the open loop transfer function from the given value. The open loop gain was given, also the cutoff frequency was given. From there you could get the open loop transfer function. Then it was made in a closed loop. Even if you don't remember any formula, you can simply derive it. Otherwise we remember the formula as well. Then this is how we could derive the closed loop transfer function, and then we simply need to put the value. Now some people will try doing it in this way, that they will say, sir, we know one thing, that gain bandwidth product is always constant. Gain into bandwidth product is always constant. So what is the DC gain? DC gain given is 10 to the power 5. 10 to the power 5. What is the bandwidth? Initially the bandwidth is 8 hertz. Now the gain they are asking at 15 kilohertz. So let's just call gain at 15 kilohertz, and frequency I can take 15 kilo here. I have seen many people doing like that, but you will get wrong answer here. What was the answer you will be getting? 8 by 15. So 53.33. 53.33 gain volt per volt. This doesn't make any sense, right? This doesn't make any sense. So this answer is wrong. There is no use of this. One more way, what can be one more way, that you know that your gain will be decreased. In the positive feedback, your gain will be, in the negative feedback, your gain will be decreased by 1 plus a beta factor. So what will be your gain with feedback? That would be, what was the initial gain? 10 to the power 5 divided by 1 plus a beta, 10 to the power 5 by 80. So this one is very less. So your gain will nearly be equals to 80 only. Now your gain is nearly equals to 80. This is your gain. Now what will be your bandwidth? Omega naught with feedback. That would be equals to, what was the initial bandwidth? 8 hertz into 1 plus a beta, 10 to the power 5 by 80. Again this value is very larger than 1. Then this bandwidth will become 8 into 10 to the power 5 by 80. So it would be 10 kilohertz. So your new bandwidth is 10 kilohertz and gain is 80. So how you can write the response now? AVS with feedback. The response will be 80 upon S by omega naught plus 1, where omega naught value is 2 pi 10k, 2 pi into 10k. This is the new value, and you need to find the gain at 15 kilohertz. So you can write f is 15 kilohertz divided by 10k plus 1, and from here you will calculate 80 upon 1.5 whole square plus 1. This is the other method of doing it. So here also you will get the approximately the same answer, 2.25 plus 1 under root reciprocal into 80. 44.37 you are getting, 44.37, and here we are getting 44.36. So this is also same. Here just we are ignoring that one value, that's it. This one value is being ignored again and again, right? Here also it was ignored. So the answer will not change much, but that you gain bandwidth product is constant, that thing you apply, then it will be wrong, right? Because 15 kilohertz that is not a bandwidth. This we are finding the gain at a particular point. It's not that for the complete graph the gain here and this point will be constant, gain here and this point will be constant, gain here and this point, multiplication of this point, these point, multiplication of these 2 points, multiplication of these 2 points, multiplication of these 2 points, that will be constant. It's not necessary. Gain into bandwidth is constant. What does that mean? That for a particular gain this was the graph, and for another particular gain, let's just say this was the graph. So what is the bandwidth you are getting here? This is the bandwidth you are getting here, and what is the bandwidth you are getting here? This is the bandwidth you are getting here. And let's just say this gain was x, this gain was y, and this bandwidth was f1, this bandwidth was f2. So x into f1 would be equals to y into f2. It's not that at every frequency and every gain, product of every frequency and every gain will be constant. No. That is wrong. Okay. So you need to take care about that. So this can be the second way of solving it. But initially what I showed, that was wrong. I have seen people doing it, gain into bandwidth equals to gain into bandwidth. Nah, doesn't make any sense. They don't even understand the meaning of gain bandwidth product. So I hope you have understood the other method. In this method, basically we are taking the approximations, nothing else. We are just taking the approximation. So I will just pause the video because it will just waste your time. So I will just pause the video and write the method 2 as well. Okay. So just pausing the video and writing the method. Yeah. So this is the method 2, right? The gain I wrote, the frequency I wrote, and just in the same thing that I taught you 2 minutes back, the same thing I wrote in a good manner. That's it. So gain with feedback I wrote, then I found the gain at 15 kilohertz. Well and good. So this was the frequency response. We expected it to be linear, but then we got to know that it is the same as low pass filter. If it is same as low pass filter, then this is how we can draw the frequency response. Then we solved a particular problem. So any kind of problem you can solve in the examination, right? So this was the exact method, complete exact method, and we got the answer 44.36 volt per volt, and this was the approximation. A very small approximation was there, right? Let's move to our next topic, that is CMRR. So take your full concentration, then only you will be able to understand it. So put your full concentration on CMRR. Okay. So we have already studied differential amplifiers, and there we studied this topic CMRR, right? So what did we define the value of CMRR there? Differential gain divided by common mode differential gain. I told you CMRR for differential amplifier is differential gain divided by common mode differential gain. But what people say, differential gain divided by common mode gain, that is wrong. Differential gain divided by common mode gain. This is not the answer. The answer is differential gain divided by common mode differential gain, right? So this is wrong, but this is correct, right? And what was the differential gain? You should be remembering all these things. You should be revising whatever that I have taught. So what is the differential gain? What was the differential gain? Differential gain was V02 minus V01 when we put both of the input as VA as Vin by 2 and VB as minus Vin by 2, right? So our gain would be V02 minus V01 divided by Vin, or you can write Vin by 2 minus Vin by 2. This was our differential gain. And what was our common mode gain? Common mode differential gain. What was our common mode differential gain? So what you were doing? V02 minus V01. But the case when you have applied your both of the input, VA equals to VB equals to VCM. So V02 minus V01 divided by VCM plus VCM by 2. You just take the average of the input and subtraction of the output. Average of the input. What is the average of the input? VCM plus VCM by 2. That would be VCM only. So this was your differential gain. Sorry, this was your common mode differential gain, and this was your differential gain. What was the differential gain? V02 minus V01 and the difference of the input, Vin by 2 and minus Vin by 2. So V02 minus V01 divided by Vin. And what was the common mode differential gain? That was V02 minus V01 divided by the average of the input, VA and VB. So V02 minus V01 divided by VCM. This was your common mode differential gain. And what was the CMRR value? CMRR value was differential gain divided by common mode differential gain. Say yes or no. Everything is crystal clear, no doubt about it. So this was the scene for the differential amplifier. But for the OpAmp as well, we can define the CMRR value. But that value is defined as differential gain divided by common mode gain. It is actually differential gain divided by common mode differential gain only. Differential gain divided by common mode differential gain only. But what is the scene in the OpAmp? In the OpAmp, output is only one. In the differential amplifier, there was two output. In this, only output is one. So in the differential amplifier, there were two output, V01 and V02. What was the common mode differential output? Common mode differential output. Common mode differential output. You apply VCM input. And in case of common mode differential output, you take the subtraction. And what was the common mode? This was common mode differential output. And what was the common mode output? You just take the average of both of them. That's it. V02 plus V01 divided by 2. Now output is only one. In both of the case, the input was same. The input was VCM only. Average of these two inputs. That's it. The input was VCM only. But output was different. Output was different because there were two output. In the first case, it was V02 minus V01. In the other case, it was V02 plus V01 by 2. But in the case of OpAmp, there is only one output. So common mode differential gain and common mode gain both are same only in case of OpAmp. Did you understand this point? Look, CMRR is defined as differential gain divided by common mode differential gain. That's for sure. But that is the definition for differential amplifier. There are two output. In OpAmp, there is only one output. What was your common mode differential output? This was your common mode differential output, V02 minus V01 with VCM as input. And what was your common mode output? V02 plus V01 divided by 2 with VCM input. They were different because there were two output. Now only one output is there. So simply what will be your common mode gain? What will be your common mode gain? That you apply V1 as VCM, you apply V2 as VCM, you calculate your output and divided by VCM. That will be your common mode gain. That's it. Common mode gain would be you apply V1 as VCM, V2 as VCM and get V0. That's it. So V0 by VCM, that would be your common mode gain. And what will be your differential gain? For differential gain, what you will do? You will apply VCM as this, V positive value as Vin by 2 and V negative value as minus Vin by 2. And then you calculate the output. So V naught by and subtraction of both of these, that would be V in only. So this will be your differential gain. That's it. This is your differential gain. This is your common mode gain. Understood? So I hope you are getting these things clear. We will discuss about common mode gain and differential gain. Here in this slide, I wanted to make one thing clear, that for the case of OpAmp, common mode differential gain and common mode gain both are same value. So in a lot of textbook, you will find CMRR to be defined as differential gain divided by common mode gain. That is the definition for OpAmp. But since this is the definition for OpAmp, many guys write the same CMRR value for differential amplifier as well. That differential gain divided by common mode differential gain. That is absolutely wrong. If there are two output, then what you need to do? First, you need to calculate differential gain, then divided by common mode differential gain. V02 minus V01 divided by VCM. Not V02 plus V01 by 2 divided by VCM. No. You are not going to take average of output. Every time you are taking the difference only. Right? So for CMRR for differential amplifier and CMRR for OpAmp, both are very, very different thing. In the first case, you had two output. In the OpAmp, you have only one output. You are getting only single-ended output. So both are very different thing. But in case of OpAmp, common mode gain and common mode differential gain is the same. So this is what I wanted to teach you in this particular slide. Now we will see what is your differential gain and what is your common mode gain for OpAmp. That is very simple. Here only you must have understood. So let's see differential gain. For differential gain, you will apply V in by 2 and minus V in by 2 and you will get some output. So what do you think what you will get? V naught, I will call it V naught D, differential output. Okay. V naught D would be AOL into V in by 2 minus of minus V in by 2. So plus V in by 2. So AOL into V in. Right. This is what you are getting. So what will be your differential gain? Differential gain I am showing as AD. That would be your V naught D divided by V in. And that would be equals to, in this case, it is equals to AOL. So this is your differential gain. Right? And what about common mode gain? So what do you think what should be your common mode output in this case? What should be your common mode output? V naught CM. V naught CM is equals to AOL VCM minus VCM. What do you get from here? Your common mode output is 0. Common mode output is 0. I should have some space. Yeah. So your common mode output is 0. This is what you get here. How your common mode gain is defined? Common mode gain is defined as common mode output divided by VCM. That's it. Look, it has nothing to do with the amplifier. What you will do? If you are finding common mode gain, what you will do? At V positive, you will apply VCM. At V negative, you will apply VCM. Then you will see what is the output you are getting. For an ideal OpAmp, you are certainly getting 0 output, right? For an ideal OpAmp, you are certainly getting 0 output. If you are getting non-zero output, what will be your common mode gain? Your common mode gain will simply be V naught CM divided by VCM. That's it. It's not that you are going to write V naught CM divided by VCM minus VCM. No. Your input is VCM. At the input, you are taking the average again. Here you are taking the difference. And at the input, here you are taking the average. Here you are taking the difference. I should show like this. And here again you are taking the average. Okay. So in case of difference common mode gain, you need to take care that you don't need to apply the OpAmp property. Your target is apply VCM. Get your V naught CM. You have your V naught CM. What will be your common mode gain? Common mode gain will be V naught CM divided by VCM. That's it. In this case, it is equals to 0 only. So what will be your CMRR? Your CMRR is common mode gain, differential gain divided by common mode gain. Differential gain you got AOL divided by 0. That would be infinity. So for an ideal OpAmp, CMRR is infinity. But practically what will happen is that even if you apply VCM voltage, even if you have applied same voltage at inverting and non-inverting amplifier, still you will get some output. Then how will you define your common mode gain? You will define your common mode gain as the common mode output that I get divided by my common mode input. That's it. You don't need to think anything. That will be your output. Did you understand this point or not? Even if I apply common mode, even if I apply the same voltage at inverting and non-inverting terminal, at inverting and non-inverting terminal, I am applying the same voltage, still I am not getting zero output. I am getting some finite output. So how will I define my common mode gain? That would be V naught Cm divided by the common mode input. That's it. V naught Cm divided by Vcm. This is how I will define it. So what will be my CMRR? CMRR will simply be common mode gain divided by what will be my CMRR. So here only I can write CMRR will be differential gain divided by common mode gain, right? So how do you usually write your OpAmp output? If I have a page where I can discuss it, let's discuss it here only. How do you usually write your OpAmp output? Like this is your OpAmp. You apply V1, you apply some voltage and you get some output, right? If you are applying V in by 2 here and minus V in by 2 here, what will be your output? Differential gain into V in, right? Or you can say differential input, differential gain into differential input, plus even if you had applied common mode input, but still you are getting some output. So what you can write? My common mode gain into my common mode input, that I am writing VCM. Did you understand this point? This is how you can express the output of OpAmp. So in the output of OpAmp, this was very general, that you would get AD into VC, differential input into the differential gain, that will be your output. But even for the common mode, you get some output. Even when there is some common mode applied, you are still getting some output. So that also you need to add. That is the known ideality. At common mode, you should get zero output, but still you are getting some output. So that also you need to get. So AD into VD plus AC into VC. Differential gain into differential voltage, common mode gain into common mode voltage. This is how it is shown. So this you can remember, right? The output of OpAmp is common mode gain into common mode input, sorry, differential gain into differential input plus common mode gain into common mode input as well. Common mode gain into common mode input, right? I hope you are getting these points. If you are not getting these points, you can get back to the video and watch it again. What I am saying is that if I apply differential input, I will get some output. Even if I am applying some common mode input, still I am getting some output. I am applying common mode input, still I am getting some output. So how I can define the output in one term? Common mode gain, sorry, differential gain into differential input plus common mode gain into common mode input. This is how I can define it. Well and good, everything is crystal clear, right? Although this expression is not that important, but the concept was important, how to find the common mode gain, how to find the differential gain, and that I hope you must have understood. For finding common mode gain, you will apply VCM, you will calculate V naught Cm, and for finding differential gain, you will apply V in by 2 minus V in by 2 and you will find V naught, right? And this is how the final output can be shown. Generally, the OpAmp output can be shown as AD into VD plus ACM into VCM, or I can write V naught is equals to differential gain into differential input plus common mode gain into common mode input. Right, so this is how it is defined. Can I write it in this manner? V naught is equals to AD into, generally what is your differential gain? Let's just say this is your OpAmp. Now differential gain, I mean to ask generally what is your differential input? This is your OpAmp. This is plus minus. This I am calling as V1. This I am calling as V2. For differential input, what you will do? You will write V1 equals to Vn by 2 and V2 equals to minus Vn by 2. Then what will be the input? V1 minus V2, right? Say yes or no. Input will be V1 minus V2. I am going to apply V1 equals to Vn by 2 and V2 equals to minus Vn by 2. My input will be Vn minus V2. Plus, I will have some common mode gain. What will be my input for common mode gain? I take the average of the input. What is the average of the input? V1 plus V2 by 2. This is how I can write it, right? This is the other way of expressing it. Sometimes this is how also you can express it. We can solve the problems on it in the assignment video. You will see some problems on it as well, so it will be all clear to you. You will not have any doubt. That's my guarantee. Okay, so common mode gain and differential gain, and then how will you define the CMRR? CMRR will simply be AD by ACM. I will tell you how to solve the problem without any confusion. So the main target is to solve the problems only, right? And the concept is also clear. What is CMRR? Generally for a differential amplifier, let's see the concept. Generally for a differential amplifier, CMRR is defined as differential gain divided by common mode differential gain. But in case of OpAmp, there is only one output, so we define it as differential gain divided by common mode gain, because both common mode gain and common mode differential gain are same only. Well and good. How will you get differential gain? For differential gain, you will apply V1 equals to Vn by 2 and V2 equals to minus Vn by 2. So, and you will calculate V naught. So V naught D divided by your difference of the input, that is Vin. That will be your differential gain. And what will be your common mode gain? You will apply common mode input at the both of the terminal, VCM and VCM, and you will calculate V naught CM. So V naught CM divided by the average of the input. So that would be VCM only. So V naught CM divided by VCM. Ideally, it should be 0. So for an ideal OpAmp, the CMRR is infinity. Okay. Then, but practically, what happens is that even if you had applied the same input, still you are getting some output. Practically. Now, why that happens? Because of the noise present in the circuit. Okay, OpAmp is a very big IC. There will be some noise present in the circuit. Because of the noise, you are getting some output. So that output is known as common mode output. You are having some common mode output. So how will you define your common mode gain? Common mode output divided by the common mode input. Common mode output divided by the common mode input. So that would be V naught CM divided by common mode input is the average of the input applied. V1 plus V2 by 2. That means VCM plus VCM by 2. That would be VCM only. And how will you define CMRR? AD by AC. So this is the scene that OpAmp output can be defined as differential gain into differential input plus common mode gain into common mode input. Right? Common mode input will be V1 plus V2 by 2 and differential input will be V1 minus V2. The CMRR will be AD by ACM. Right? Now there is a point I have written. Generally CMRR is defined for the open loop configuration of OpAmp. That I am saying that CMRR of OpAmp is 90 dB. I am saying that CMRR of OpAmp is 90 dB. So what does that mean? I am defining it for the open loop. I am defining the CMRR for this configuration. That's it. But even if we connect some feedback or these things, like these things, even if we connect, this is the differential amplifier, R2, R1, R2, R1. So for that case as well, the CMRR is same. We generally take the CMRR for the complete configuration, same only, whatever that we get for this particular IC. Okay. But if R2, R1 values are different, then there can be some issue. So we will see both of the question. This point will be more clear once we move towards the question. Okay, more clear it will be. So let's see the questions now. So first question we will take. This is the question. You are given differential input. The common mode configuration is given. VCM is given. Common mode input is given. That at both of the terminal 2 millivolt and 2 millivolt is applied. CMRR of the OpAmp is given. That is 90 dB. You need to find common mode output voltage if you are applying 2 millivolt and 2 millivolt here. So if you are applying 2 millivolt and 2 millivolt here, what you should get at the output? Check the ratio. Same? Yeah. The ratio is same. 1 by 10 is equals to 1 by 10. So what I told you, I can apply RF by R, 10K by 1 into V2 minus V1. What is V2? 2 millivolt. minus 2 millivolt. Ideally, your common mode output should be 0. But that would be the case if your OpAmp is ideal. But your OpAmp is not ideal. OpAmp is having CMRR of 90 dB. So this is the issue here. Okay. So let's solve the problem. What I will write is that if OpAmp was ideal, so what will be your V0 CM? That would be 10K by 1K VCM minus VCM. That would be equals to 0. But OpAmp is having CMRR equals to 90 dB. CMRR equals to 90 dB, right? CMRR equals to 90 dB. So how will you show it in decimal? The CMRR is 90 dB. So how it will be there in decimal? 20 log 10 CMRR. In deci I am writing in decimal. That is equals to 90 dB. So 10 to the power 4.5, right? This 20 will go here, that would become 4.5. So 10 to the power 4.5, that will be a large value. 4.5 10 to the power. So CMRR will be in decimal. CMRR will be, I hope you understood this point, right? CMRR is 90 dB. In decimal, what it will be? 20 log 10 into x. 20 log 10 x. X is CMRR only, but in decimal. So 90 by 20. So that would be 31622.78. This is the CMRR in decimal. Okay. This is the CMRR value is given. That means this is the CMRR value is given. Now can you find differential gain? Differential gain. And this CMRR is defined as differential gain divided by common mode gain. What is the differential gain? What will be the differential gain? Or this we need to find. So better first calculate differential output. Differential output. That would be RF by R 10 by 1K, 10K by 1K, V2 minus V1, V2 minus V1. But V2 minus V1 is 5 millivolt. So V2 minus V1, 10 into 5 millivolt. That would be 50 millivolt. And what is your differential input? Differential input is also 5 millivolt. Differential input is V2 minus V1. That is 5 millivolt. So what will be the differential gain? Gain AD. That would be 50 millivolt divided by 5 millivolt. Always solve these problems step by step so that you don't make any error. So differential gain is 10. Otherwise you can also see RF by R differential gain will be 10 only, right? RF by R V2 minus V1. So what will be your differential gain? Differential gain will be differential output divided by differential input. Differential input is V2 minus V1. Differential input is V2 minus V1, right? So what will be the differential gain? 10 into V2 minus V1 divided by V2 minus V1. So it would be 10 only. So differential gain would be 10 only. That is very clearly seen here. But still I wrote it so that you don't get confused. Anywhere you are not getting confused, we are writing every single step so that in the examination we don't do any mistake. So differential gain you have. Differential gain divided by common mode gain, that is equals to, it is given 31622, 31622.78. So differential gain is 10 divided by common mode gain, 31622.78. From here we will get common mode gain. So reciprocal into 10. So this we are getting 3.16 into 10 to the power minus 4. This is the common mode gain we are getting. Common mode gain. This is the common mode gain. What is the common mode input? Common mode input is 2 millivolt. Common mode input is 2 millivolt. So this is the common mode gain. Common mode gain. So what will be your common mode output? Common mode output divided by common mode input. Common mode input. That is equals to your common mode gain. So your target is to find common mode output. That would be equals to 3.16 into 10 to the power minus 4 into common mode input. What is the common mode input? Common mode input is 2 millivolt. Common mode input is 2 millivolt into 2. 6.32 into 10 to the power minus 7. So 0.632 microvolt. This is your common mode output. So your common mode output was 0.632 microvolt. This was your common mode output. This is the final answer. Did you understand what we did here? If your OpAmp was ideal, your common mode output would have been 0. Your common mode output would have been 0 if OpAmp was ideal. But OpAmp was not ideal. OpAmp was having CMRR of 90 dB. What does that show? That certainly there will be some common mode output. If common mode output is 0, then it would have been infinity, but it is some finite value, so certainly there is some common mode output, right? Then we go to know what is my differential output. Sorry, what is my differential gain? My differential gain is 10. So what will be my common mode gain? My common mode gain will be very, very less. It will be some 3.16 into 10 to the power minus 4. So this is my common mode gain. So what if I have the common mode gain? I can find the common mode output because I already have the common mode input. The common mode input is 2 millivolt. So from the common mode input 2 millivolt, I could get the common mode output. That's it. This was the particular question. Now we will solve one more gate question. This was asked in gate 1996, which is a very good question. Here the OpAmp is ideal. The OpAmp is ideal. Now they are asking you the CMRR of this particular differential amplifier shown. The OpAmp is ideal here. Now they are asking the CMRR of this differential amplifier that is shown here. How will you calculate it? Tell me. The same method. First we are going to find differential gain. The second method and the second thing we are going to find common mode gain. So let's find the differential gain first. Let's copy this circuit and find the differential gain. I told you there is simple method. Whenever there is differential amplifier, what we need to find? Differential gain. First target is to find differential gain, that is your AD. For that, I will copy the circuit and what I will apply at the input. At the input, I am going to apply Vin by 2 and minus Vin by 2. Towards the positive side, I am going to apply Vin by 2. And towards the negative supply, I am going to apply minus Vin by 2. Here, this OpAmp is ideal. This is having CMRR equals to infinity. But these resistances, these are not equal now. So even if you apply common mode VCM here, you are going to get some output. So that is the issue now. Can you apply V0 equals to RF by R 100 by 1K into Vin by 2 minus Vin minus of minus Vin by 2? Can you apply this? No, this is wrong. You cannot apply it. So what I need to do? I will apply superposition theorem. So directly I am going to write now. What will be my V0? First I am considering only Vin by 2. So what will be my V0? 90 by 91 into Vin by 2. This will be the potential here. Then it would become non-inverting amplifier into 1 plus RF by R. 1 plus RF by R. 10 by 100 by 1. Then other one. This I will, now I am going to consider only this one. So if I consider only this one, what will be the gain? Minus RF by R into minus Vin by 2. Right? So that would be 90 by 91 into 101 plus 100 90 by 91 into 101 plus 100. The bracket you are having, this is your V naught. This I can call V naught D. V naught D. So what will be your differential gain? What will be the differential gain? That would be V naught D by V in, not V in by 2. Your differential gain would be V naught D by V in. So what is your differential gain? Differential gain would be V naught D divided by V in. That would be 90 by 91 into 101 plus 100 divided by 2. 99.94. 99.94 volt per volt. You need just take care of this. Sometimes people calculate V naught D by V in by 2. No. V naught D by V in, because the differential output divided by the difference of the input. That would be V in by 2 minus of minus V in by 2. So V naught D divided by V in. That would be the differential gain. Well and good. 99.94. This is your differential gain. Now we are going to calculate common mode gain. So let's calculate common mode gain now. VCM and VCM. This is the common mode output. That would be 90 by 91 into 1 plus RF by R into VCM. 90 by 91, what that will be the potential here, into VCM, into this will become a non-inverting amplifier. If it is a non-inverting amplifier, that will give a gain of 1 plus RF by R. Plus, now I am going to consider only this VCM, this will be grounded. So that would be RF by R into minus VCM. Sorry, RF minus RF by R into VCM. So that would be minus RF by R into VCM. So 90 by 91 into 101. 90 by 91 into 101 minus 100. There is some issue, I guess. 1 plus, how I am getting negative value? Again, let me check. 90 by 91 into 101 minus 100. Okay, you will get negative only. Minus 0.109. This is your V naught CM into VCM. So what will be your common mode gain? ACM. I told you that would be the common mode output divided by the average of the input. That will be VCM only. So common mode output divided by the average of input. So that would be minus 0.109. So my common mode gain is minus 0.109. So it's good that I am getting in negative, because I told you to, I forgot to tell you one thing. This CMRR is wrong. Actually, this CMRR is the magnitude. Okay, this CMRR is the magnitude. Anywhere else I wrote it. Yeah, always you need to take the magnitude. I'm sorry that I forgot to tell you this. Anywhere I wrote it. Yeah, differential gain divided by common mode gain. Here also always you need to take the magnitude. CMRR is always defined positive in case of decimal. In case of dB it can be negative, but it is never negative, because AD is always very high. So it is always defined positive. So AD by AC you should always take the magnitude. Okay. So what will be your CMRR now? AD by AC it will be. So CMRR would be AD by AC 99.94 divided by AC, that would be minus 0.109. Always you need to take the magnitude. So take the reciprocal into 99.94 plus minus. So it is coming around 909.45. This is the CMRR value. Okay, you can calculate it in dB as well. So how will you do it in dB? 20 log 10, 909.45, right? So let me calculate it in dB. Yeah, so in dB you are getting nearly around 59.17. So if they ask this question in numerical answer type, they will certainly ask it in dB only, because the range will be lesser. Because some people would have calculated 900 as answer, some would have calculated 890 as answer, because there are a lot of calculation involved. So sometimes there the range increases, but in dB the range will be lesser. So in the examination there is high chances that they will ask in dB, but you should be aware what they are asking, okay, in dB or in decimal. So in decimal it is 909.45, and in dB it is 59.17 dB. Okay, so this was the CMRR. What was the difference in both of the problems? The circuit was same. In both of the problems the circuit was same. In this one, in the previous one, what was the first problem? Yeah, this was the first problem only. Here RF by R was same. So ideally we should have got VCM equals to 0. But here the OpAmp was non-ideal. It was having some CMRR. If it was having some CMRR, then certainly you are having some common mode gain. So that common mode gain we calculated, and from there we could calculate some common mode output. Ideally the common mode output should have been 0. But from the given question we calculated the common mode output. In this case, the OpAmp is ideal. It is having CMRR equals to infinity. But the configuration is not the ideal differential amplifier configuration. If it was the ideal differential amplifier configuration, that means RF by R would have been the ratio of this to this and this to this would have been same, but it is not the same here. So there will be some common mode output as well, there will be some differential output as well. Simply the question is, this particular black box is given, two inputs are applied, V1, V2, and you are having some output. If you are applying differential input, you are getting some differential output. If you are applying some common mode input, you are getting some common mode output. That's it. So this particular configuration was there. We applied differential input, we got differential output. That was V0 D by V in, that was 99.94. We applied common mode input, we got some common mode output as well. So common mode output was 0.109 into VCM. So what will be the common mode gain? That was minus 0.109. Then we could calculate the CMRR value. In dB it was 59.17 dB. Well and good, everything is crystal clear. Let's move towards our next and the final known ideality or the parameter of OpAmp, that is slew rate. So forget about the definition. The definition I have written, maximum rate of change of output voltage. Forget about it. Let's understand it by the example. So let's say someone is saying your slew rate is 5 volt per microsecond. So what does it mean? That it means that it takes 1 microsecond for the output to reach to 5 volt. Let's just say your output is going from 0 to 10 volt. So it will take it 2 microseconds from reaching from 0 to 10 volt. Did you understand this point? It takes 1 microsecond for the output to reach to 5 volt. From 0 to 5 it will take 1 microsecond. From 2 to 7 how much time it will take? 1 microsecond. From 2 to 17 how much time it will take? It is rising 15 volt. It is taking 15 volt. So if it is taking 15 volt, that means it would require 3 microsecond. So from 2 to 17 if it is going, it would take 3 microsecond, right? If it is going from 17 to, not 17, let's just say it is going from 27 to 2 volt. So how much voltage it is losing? 25 voltage it is losing. So for losing 5 voltage it takes 1 microsecond. So losing 25 voltage it would take 5 microsecond. So if it is coming from 27 to 2, it would take it 5 microsecond, right? So this is what it means. So what does it mean? That if your slew rate is 5 volt per microsecond, that means it would take the output to reach to 5 volt. It would take 1 microsecond time for the output to gain or lose 5 volt. If your output is increasing from 0 to, let's just say, if your output is increasing from 0 to 5 volt, 0 volt to 5 volt, it would take it 1 microsecond. Or if your output is increasing from 0 volt to 10 volt, 0 volt to 10 volt, it would take it 2 microsecond. If your output is decreasing from, let's just say, 17 to 2 microsecond, 17 volt to 2 volt, sorry, 17 volt to 2 volt. So 15 volt it is losing, so it will take 3 microsecond, right? So these are the ways. This is how you can understand the slew rate. So isn't it the slope only? So slew rate, what is the slope here? 5 volt divided by 1 microsecond. 5 volt divided by 1 microsecond. 5 volt per second. What is the slope here? 10 volt divided by 2 microsecond. It is also 5 microsecond. What is the slope? I am asking what is the slope? 5 volt divided by 1 microsecond. This is the slope. What is the slope here? 10 volt divided by 2 microsecond. So it will also be 5 volt divided by 1 microsecond. And what is the slope here? It could be negative, although it is negative slope. So I can write 15 volt divided by 3 microsecond. So it is also 5 volt per microsecond. The slope is the same. So generally the slew rate is defined as dV naught by dt. Not T, I should not write. dV naught by dt. So this is how the slew rate is defined. So we will understand this particular problem. We will understand this particular known ideality or the parameter by the questions only. So let's solve a particular problem that is not depending on it is not depending on OpAmp or anything. We just need to find slew. Find slew rate. Find slew rate. This is the question. Find slew rate considering your output to be VCT. So one method is to just write the formula. The slew rate is dV naught by dt. So let's just see method 1. So what is the slew rate? Slew rate is dVc by dVct by dt, you can write. This is what you need to find, right? What do you know? It is equals to C dVct by dt, right? What will be your dVct by dt? That would be IT by C, or you can write 5 ut by C, or basically it is 5 by C. So your slew rate is 5 by C. 5 by C is 2 farad. 5 by C. So that would be 2.5 volt per second. Or how will you understand it? This is simply the formula. Let's understand it by the method. So what is your VCT voltage here? VCT voltage is 1 by C integration from 0 to T IT dot dt. The current is constant, so it would be 1 by C is 2. Current is constant, so you can take it outside. 5t ut. This will be the final answer. Or you can write your VCT would be 2.5t ut. This will be your VCT, right? 2.5t ut. So basically this is your VCT. So how will the VCT waveform go? VCT waveform will look something like this. VCT versus T. This is how the VCT waveform will go. So in 1 second, how much the voltage you will get? 2.5 volt. In 1 second you will get 2.5 volt, right? 2.5 volt you will get in 1 second. So in 1 second you are getting 2.5 volt. So what will be the slew rate? 2.5 volt by second. In 2 seconds, how much voltage you will get? 5 volt. So what will be the slew rate? 5 volt by 2 microsecond. 5 volt by 2 second. That means 5 volt by 2. What I mean to say is that you are getting 5 volt in 2 seconds. So it would be 2.5 volt per second. So your slew rate is 2.5 volt per second. So in 1 second you gain 2.5 voltage. That's it. This is the actual math. This is the actual way of understanding it. This was just a method that your slew rate is defined at the slope of the output. Slope of the output. That's it. This is the slew rate. So slope of the output will be I by C. So 5 by C. 5 by 2. 2.5 volt per second. This is the slew rate. But actually, if you draw the output waveform, you would get to know that in 1 second I am getting 2.5 volt. So my slew rate will be 2.5 volt per second. I hope it is crystal clear to you. What do you mean by slew rate? But generally, the unit of slew rate for OpAmp, slew rate unit is generally it is in volt per microsecond. That it would take it some microsecond to reach a particular voltage. Generally, it would be 5 volt per microsecond. That means for the OpAmp output to reach 5 volt, it would take it 1 microsecond. Okay, so generally this is the unit, volt per microsecond, not volt per second. This is just an example I took. For OpAmp, it is volt per microsecond. Okay, not volt per second. Let's see this example. I will pause the video and take a break. Then I will proceed. Okay. Okay, so let's start again. So you need, this is the question. This is a simple voltage follower circuit. You need to draw the V0 waveform for Vx equals to 5 volt and Vx equals to 10 volt. You need to take slew rate equals to infinity. For an ideal OpAmp, slew rate is infinity. Let's understand the meaning of slew rate equals to infinity. So slew rate is equals to infinity volt per microsecond. So it can be some voltage per 0 microsecond. Say yes or no. So what does it mean? It takes OpAmp to reach any particular voltage in 0 microsecond. The OpAmp can reach any particular voltage in 0 microsecond. This is what it means. Because when we were studying ideal OpAmp, I did not teach you any concept of slew rate. That means what will be your output here? V0 is equal to simply V in. So whatever the input you are getting, the same output you will get. That's it. So this will be the answer only. But the slew rate is infinity. What does that mean? That it takes 0 microsecond for the OpAmp to reach any particular voltage, be it 5 volt, 10 volt, 15 volt, 1000 volt, 1000 volt, 1 millivolt, 1 megavolt, 1 kilovolt, or any voltage. In 0 microsecond, it will reach. That means immediately it can reach. Say yes or no. Right? Output will simply follow the input. So what will be the answer for E? So your output waveform will simply the same as input. कोल्ड हो गया भाई बार बार. The reason I have to pause the video again and again is that I am getting some cold. That's why. Okay, ये बैंगलोर का वेदर ना बड़ा अजीब सा हो गया अभी. From 0 to 5 volt it will rise in 0 microsecond. And what will be the answer for B? In 0 microsecond only it will rise from 0 to 10 volt. So these topics are actually very complex to understand, but we will take example and we will make everything very, very easy, right? Let's take the second question now. Now the slew rate is 0.5 volt per microsecond. Okay, this is the slew rate. You need to draw the V0 waveform for 5 volt and 10 volt. You know one thing, that V0 is equals to V in. This is what you know. First thing you know is that your slew rate is 0.5 volt per microsecond. And the second thing you know is that your V0 is equals to V in. Right? So your output will follow the input, but input is rising from 0 to Vx voltage in 0 time. 0 to Vx voltage in 0 time only. But here it will take you finite time. So for rising 5 volt, how much time it will take? 10 microsecond, right? So what will be the answer of A? Your output will be V0 will be equals to V in. It needs to rise from 0 to 5 volt. 0 volt to 5 volt. But it will take some time from 0 to 5 volt. From 0 to 0.5, it would take 1 microsecond. From 0 to 5 volt, it would take 10 microseconds. Right? From 0 to 5 volt. Draw the output for V. You need to rise from 0 to 10 volt. It will rise like this. Yeah, so V naught is rising from 0 volt to 10 volt and it will take it 20 microsecond, right? Because slew rate is 0.5 volt per microsecond. That means it would take it 1 microsecond to reach 0.5 volt. That means it would take 20 microsecond to reach 10 volt. So this would be 20 microsecond. Well and good. Let's see the next question. So the same question is there, the same circuitry is there. Now the input is square wave. Vx to 0, Vx to 0, Vx to 0. This is the input. Vx 0, Vx 0. This is the input. Slew rate is 0.5 volt per microsecond. You need to draw V naught for Vx is 5 volt, Vx is 10 volt, Vx is 20 volt. Well and good. And this window you are having is 20 microsecond. This small window, that is 20 microsecond. So what will be your output voltage? This is what we need to draw. So what do I know? My slew rate is 0.5 volt per microsecond. So in 1 microsecond we will gain 0.5 volt. Right? So first is Vx equals to 5 volt. So let's copy it and paste it here. Vx equals to 5 volt. 5 volt, 5 volt and 5 volt. And the other thing I know is that my V naught is equals to V in only. V naught is equals to V in only. V naught is equals to V in. So my output should reach 5 volt. How much time it will take? My output to reach to 5 volt. It would take 10 microsecond, right? In 1 microsecond I am getting 0.5 volt. So in 10 microsecond you will get 5 volt. In 20 microsecond you will get 10 volt, right? So I will get in 10 microsecond only I will get to 5 volt. In 10 microsecond I will get to 5 volt and then I will remain there. Then output will remain at 5. Then again my output will try to go to 0. My output will try to go to 0, but it will take it 10 microsecond. Then again after 10 microsecond it will remain there. Then again my output is trying to go to 5 volt again, but it will take it 10 microsecond. It will remain at 5 volt only, but again my input is 0 volt. Then again my output is trying to go to 0 volt. Output is trying to go to 0 volt. Output is simply following input. Output is simply following input. Input is being from 0 to 5 volt, but for output it will take it 10 microsecond. 10 microsecond, 10 microsecond, 10 microsecond and 10 microsecond. Then again it is following. Then again 10 microsecond. So a trapezoidal shape you are getting. Trapezoidal shape you are getting. Right? So this is a trapezoidal shape you are getting. This is a 0. This time is 10 microsecond. This time is 30 microsecond. This time is 40. This time is 50 microsecond. This time is 50. This time is 70 microsecond. And so on. So this is a trapezoidal shape that you are getting. Right? So this is the output waveform. This is the output. Let's see the second question. In the second question, your Vx is 10 volt. Your Vx is 10 volt. So how much time it will take for output to rise to 10 volt? 20 microsecond. In 20 microsecond, it will rise to 10 volt. So what will happen is that output is following the input. So input is saying that I am going to 10 volt. So what output will say? Output will say I will also go to 10 volt, but it will take me 20 microsecond. So here I reached to 10 volt. Just as it reached 10 volt, what input will say that I am going to 0 volt. So output will also say that I am also going to 0 volt, but it will take me 20 microsecond. Just as it has reached here, now what will input say? Input will say that now I am going to 10 volt. Output will say I will also go to 10 volt, but it will take me 20 microsecond. Then it will say again it will take me 20 microsecond. Again it will take me 20 microsecond. So it is reaching to 10 volt, but it is never staying there. It is reaching to 10 volt, but it is never staying there. Immediately input is saying that I am going down, right? So this is your output waveform. So output waveform is trapezoidal. Sorry, here it is triangular. In the previous case, output waveform was trapezoidal. What will happen in the last case? Twenty volt, 20 volt, and 20 volt. Right? So what will output say? That input is saying that I am going to 20 volt, but the output will say that it will take me 40 microsecond to reach 20 volt. How much time it will take? It will take me 40 microsecond to reach to 20 volt. So the output is trying to reach to 20 volt, okay, in 40 microsecond. It is trying to reach to 20 volt. Just here at 20 microsecond, what input will say? That I am going to 0 volt now. The output will say I will follow you, so I also need to go to 0 volt. The output is saying that I need to follow you, so I will also go to 0 volt. In 20 microsecond, it has only reached to 10 volt. It was trying to go to 20, but it has only reached to 10 volt. Now input is saying that I am going back to 10 volt. I am going back to 0 volt now. I need to go to 0 volt. So what output will say that I will also go to 0 volt. I am going to 0 volt, but output needs 10 microsecond to go to 0 volt, because it is at 10 volt. Now it needs to go from 10 volt to 0. So how much time it will take? It needs to go from 10 volt to 0 volt. How much time it will take? For losing 10 volt, it needs to take 20 microseconds. So output will say that I need 20 microseconds. So in 20 microseconds, it will come down to 0. Now what input will say? That again I am going to 20 volt. So output will say that okay, I will follow you. I also need to go to 20 volt. So again it is trying to follow the input. But what will happen? In 20 microsecond window, in this window, it will only reach to 10 volt only. Then again the input will say that I am going to 0 volt. Then again output will say I will have to follow you, but it will take me 20 microsecond to go to 0 volt. So this is how the waveform will look like. So the waveform here, the waveform and both of the waveform will be same. 0 to 10 volt, 10 to 0, triangular waveform. Same waveform will be same. Although the input is different, but the waveform will be same because of the slew rate, right? So here also the waveform will be triangular, right? I'm really sorry for the interruption in between. I have to take the break because I'm having severe cold now. Don't know what happened suddenly. लगता आइसक्रीम खाली थी आज, उसका फर्क पड़ रहा है. Okay, yeah. So let's revise the question once again. This was the particular question. There was 3 questions involved in this question. The square wave was given 0 to 5 volt it was going, 0 to 10 volt it was going, and 0 to 20 volt it was going. The slew was 0.5 volt per microsecond. So in 1 microsecond you get 0.5 volt. So for 5 volt you need 10 microsecond, for 10 volt you need 20 microsecond, and for 20 volt you need 40 microsecond. So you are going from 0 to 5 volt. You are going from 0 to 5 volt. Output is simply following the input. So output is going from 0 to 5 volt. Right? Output is going from 0 to 5 volt. Output is going from 0 to 5 volt, but it will take 10 microsecond to reach. So 0 to 5 volt, 10 microsecond. Then it will remain there. Then input is saying that I am going from 5 volt to 0. So output will also say that I will also go from 5 volt to 0, but it will take me 10 microsecond. Then it will remain there. Now again input is saying that I am going from 0 to 10 volt. Input is saying that I am going from 0 to 5 volt. Output will also say that I am going to 0 to 5 volt only, but it will take me 10 microsecond. Then it will remain there. Then 0 and remain there. Trapezoidal shape you get. The next one, the input is going from 0 to 10 volt. Output will say I will follow you. I will also go from 0 to 10 volt, but it will take me 20 microsecond. So it takes it 20 microsecond. Then what will input say? Input is saying that I need to go from 10 volt to 0 volt. Input is saying that I need to go from 10 volt to 0 volt. So output will also say that I need to go from 10 volt to 0 volt, but it will take me 10 microsecond. So it is coming, sorry, 20 microsecond. It will take me 20 microsecond because for gaining 10 volt and 20 volt, for gaining 10 volt, it requires 20 microsecond. So it is coming 20 microsecond. Now the next input, that was 0 to 20 volt. So what output will say that I am going from, input will say that I am going from 0 to 20 volt. So output will say I will also follow you. I also need to go from 0 to 20 volt, but it will require me 40 microsecond. In 10 microsecond it has reached to 10, in 20 microsecond it has reached to 10 volt. Output was trying to go from 0 to 20 volt, but for that it requires 40 microsecond. In 20 microsecond it has reached to 10 volt. Just as it reached to 10 volt, what input said that I am going to 0 now. So output will say I will also go to 0. There is no chance, I will have to follow you. So output is also going to 0, but output needs 10 microsecond time to go to 0. So output say that, sorry, 20 microsecond time. So output says that I need 20 microsecond time to go from 10 volt to 0 volt. So it is coming to 0 volt. Then input is saying that I am again going to 20 volt. Then output will say again I will go to, again I will follow you, but I require 40 microsecond. But it has the only window of 20 microsecond, so it has reached to 10 volt again. Now what output will say? The output will say that I will again have to follow the input. Input is saying that I am going from 20 volt to 0 volt now. So output has come to 10 volt only. So output will say I will also go to 0 volt, but it will require me 20 microseconds. So again it is requiring 20 microseconds. So this cycle will go on and you will have a triangular output. Well and good. So this was the question, right? Yeah, so by this way we have understood the slew rate. Let's just see one more point. What is that point? So in case of a sinusoid input, let's just say you have a sinusoid input and you want a distortionless output. So for that there is a condition that the magnitude of dV naught by dt should be lesser than the slew rate or equal to the slew rate. Slew rate should be high. What do you understand by that? Let's just say your output is sinusoid like this. If the input is sinusoid, the output will be, let's just say this is your output sinusoid, which has a peak amplitude of A. This output sinusoid has a peak amplitude of A. So your output is A sin omega t. This is your output. Okay, A sin omega t, this is your output. Now if slew rate is high, if the slew rate is low, what if the slew rate is low? Let's just say your slew rate is 1 volt per microsecond and your rate of change of output is 2 volt per microsecond, because output is sinusoid. So sinusoid also changes. Sinusoid also have some frequency, no? This also has some frequency. So based on that, what is the change of output? dV naught by dt I am saying. That is 2 volt per microsecond. And this is the slew rate. So what OpAmp is saying? OpAmp is saying that I need 1 microsecond to reach to 2 volt. Sorry, I need 1 microsecond to reach to 1 volt. And output is saying that I am running such that in 1 microsecond I am gaining 2 volt. In 1 microsecond I am gaining 2 volt. Let's just say this is 1 microsecond only. So output is saying that in 1 microsecond I am gaining 1 volt, but OpAmp is saying that in 1 microsecond I can only give you 1 volt. So there will be distortion in the output, no? The output will not be able to rise till 2 volt. It will be able to rise till 1 volt only. The same thing that happened here. This is the case of distortion, right? Here there is no distortion. Here at least it has reached to the output voltage. It has reached to the 10 volt. But here it could not even reach to the final peak value. It wanted to reach to 20 volt, but it wasn't able to reach it because the slew rate was lesser. If the slew rate was higher here, let's just say our slew rate was 0.5 volt per microsecond, right? If the slew rate was 2 volt per microsecond, 2 volt per microsecond, then how much time it would have taken to reach to 20 volt? 10 microsecond, right? In 10 microsecond, it would have reached to 20 volt. So here only it would have reached. Here only it would have reached. But our slew rate was less. So always slew rate should be high than the dV naught by dt. If you are not able to understand, you just need to remember this. Otherwise, you would have understood by the example as well that your slew rate is lesser and output is running fast. Then OpAmp will not be able to catch the output. OpAmp will not be able to catch the output if your output is running fast. So your output should run slow. Your dV naught by dt should be lesser than the slew rate. So this is the condition that is asked many times. A lot of questions are asked from this condition. So let's just say your output is A sin omega t. Let's just say your output is AM sin omega mt. So what will be the magnitude of output? dV naught by dt maximum, that would be AM omega m, right? AM omega m. The magnitude, what I mean to say is that what did I do? First I differentiate it. So what do I get? AM omega m sin omega mt. So what will be the magnitude now? What will be the magnitude? Magnitude will be this value only, no? AM omega m. This will be the magnitude. So this should be less than the slew rate. So AM omega m. Omega m you can write 2 pi Fm. That should be less than slew rate. So value of Fm you get is slew rate divided by, this should be less than slew rate. 2 pi AM. So what is the maximum value of Fm? That is slew rate divided by 2 pi AM, right? Sometimes this frequency is known as power bandwidth. Sometimes you can see it, the word that is written is power bandwidth. Sometimes this frequency is known as power bandwidth. Sometimes this name is also written, find the power bandwidth. Okay, so slew rate, this Fm should be this value, slew rate by 2 pi AM. You don't need to remember it, you just need to remember this one. Just remember this one, that if your output is running fast, it will not be able to catch, OpAmp will not be able to catch the output. So dV naught by dt should be lesser than the slew rate. This is what you need to remember. So what is dV naught by dt? You can differentiate it there. You could get to know the dV naught by dt value, that should be less than slew rate. Slew rate will be given and values will be given. You just need to find the other value. So let's see an example. This is the example. Your OpAmp slew rate is 2 volt per microsecond. So slew rate is given as 2 volt per microsecond. Your peak output voltage is 12 volt. Maximum allowable frequency of the input. Maximum allowable frequency of the input over the power bandwidth. So peak output voltage is 12 volt. 12 volt is the peak output voltage. So what is actually your dV naught by dt? dV naught by dt max, AM into omega m, right? Or you can say that my dV naught by dt would be AM omega m sin omega t. So what will be my dV naught by dt max? That would be AM into 2 pi Fm, right? My peak output voltage is 12 volt into 2 pi Fm. Power bandwidth or the maximum allowable frequency I need to find. So maximum allowable frequency. So I just need to equate it to the slew rate. Or I can say that this should be lesser than the slew rate, 2 volt per microsecond. So Fm would be Fm maximum, that would be 2 volt per microsecond. So 2 into 10 to the power 6 volt per second, right? 2 into 10 to the power 10 to the power minus 6, that would go upward. So 2 into 10 to the power 6 volt per second divided by, this 12 is volt only, so volt to volt will get cancelled. So hertz value you will get. So divided by 12 into 2 pi. That's it. 2 into 10 to the power 6, 12 into 2 pi. So from here, what do I need to calculate? 12 pi reciprocal. 12 into pi reciprocal of that into 10 to the power 6. So 26.52 kilohertz. So that is the power bandwidth. This is the answer. So maximum allowable frequency of the input should be 26.52. Because input and output is having the same frequency. This is what is assumed. Input and output is having the same frequency because OpAmp will just provide a gain. It will not change the frequency. It will not change the frequency component. It will just provide the gain. So input and output are having the same frequency. So Maximum allowable output frequency is 26.52. The same frequency that is allowable at the input will be 26.52 kilowatts. Well and good. Let's see one more question. Try solving it on your own, then see the solution. So let's see this question. So again, this question is based on your dV node by dt should be lesser than slew rate, right? This you always need to remember. People generally remember that dV node by dt should be equals to slew rate. Then in the examination they get confused that slope of output should be large or slew rate should be large. Slew rate should be larger. Okay, slope of output need not be larger. Slew rate should be larger so that OpAmp is able to catch the output voltage. So slew rate should be larger. Okay, so dV node by dt should be lesser than slew rate, because in the examination they can ask you anything. They can frame a MSQ and they can ask you what all are the frequencies which will produce that distortionless output. So for that the lesser condition will be applicable. So be aware of that. You will see these kind of question in the test series. Okay, so you should remember that there will be lesser sign. Which one should be lesser? dV node by dt should be lesser. So what is the value you will get? You already know am omega m we are getting. So am omega m should be lesser than slew rate. So what is the value of am? Am we need to find into omega m, that is 2 pi fm. Fm is 1 mega. 1 mega. That should be largest amplitude they are asking. So should be lesser than slew rate. Slew rate is 5 volt per second or 5 into 10 to power 6 volt per second. So it is 5 volt per microsecond, right? So this and this will get cancelled. So am should be lesser or equals to 5 by 2 pi. So am should be lesser or equals to 5 by 2 by pi, 0.79 volt. So what is the maximum amplitude allowable? Am max, that is 0.79 volt. This is the maximum allowable amplitude. Okay, this is the answer. So we have studied a lot of known idealities. So let's make a table now. So here write parameter, and what is the parameter? What is the value of that parameter for ideal OpAmp? And what do you get practically? Okay, so this is what we are going to write. So let me make the table. Okay, so what should be the offset voltage for an ideal OpAmp? It should be 0 volt, right? There should be no offset, but practically it is from 0 volt to some microvolt. What should be the bias current? Ideally it should be 0, but practically when you see it is some microamp to femtoamp. Offset current, again it should be 0, but again it is some nanoamp to femtoamp. Always you find some offset current. All these offsets should be 0, right? Any offset should not be there ideally. For ideal OpAmp, what is the bandwidth? Bandwidth of the OpAmp, that is infinity. But practically what is the bandwidth? Even I don't know, I need to check. So I checked for IC741 OpAmp. So there are different kind of OpAmp, okay? So there is 741 OpAmp as well. There is one IC name that is 741. So for that I checked, that is 1 megahertz. So I am writing 1 megahertz only, but for IC741. I don't know what is the typical range, because I did not work on OpAmp till now. Okay, I'm not working on OpAmp till now. When I work on OpAmp, I will get to know about it. So for IC741, that is very common IC that everyone uses. So that is, for that the bandwidth is 1 megahertz. So till 1 megahertz it will provide you the gain of A, or from A to A by root 3. So then it will start rolling off. So for that it is 1 megahertz. Okay, and CMRR it should be infinity, right? Common mode gain should be 0, but typically it is in some 100 dB, some 100 dB, near to some 100 dB. Typically this is the range. Slew rate, it should be infinity. OpAmp should have, in no time OpAmp should get any output voltage, but typically it is in some range of some, I am writing some volt per microsecond, some volt per microsecond. So it is in the range of volt per microsecond, some volt per microsecond you will get. 0.5, 1, 2, 3, 4, 4 volt per microsecond, 5 volt per microsecond, 0.5 volt per microsecond. So some volt per microsecond. So these are the practical values. These they will not ask in the examination, but this they can ask. That ideally what should be the CMRR of the OpAmp, ideally what should be the slew rate of the OpAmp, ideally what should be the bandwidth of the OpAmp, ideally what should be the Rin of the OpAmp, what should be the input resistance of the OpAmp, infinity, what should be the output resistance of the OpAmp, 0, what should be the gain of OpAmp, infinity, right? So all those things we have already seen, and these things we saw in the 2 lectures, right? So we studied about offset bias current, offset voltage, we studied about bandwidth, we studied about CMRR, and we studied about slew rate. So do revise this lecture and everything will be crystal clear to you. Okay, then let's meet you in the next lecture with the very interesting concept, that is the concept of integrator and differentiator. Okay, then thank you.